はい、皆さんこんばんは。リクルートコミュニケーションの大石と申します。今回はですね、RCO スタディナイトの特別講演といたしまして、D-Wave が切り開く、量子コンピューター活用の未来ということで、カナダでですね、リクルート、D-Wave システム社の、方に、お迎えいただきまして、開催をいたします。遅い時間に、ですけどね、多くの方がお集まりいただきありがとうございます。今回開催にあたりましてですね、RCOテクノロジーズですね、大変ご尽力いただきまして、この場開催されてますので、この場を借りて、お礼申し上げたいと思います。本日ですね、早稲田大学高等研究所にお会いしますので、よろしくお願いいたします。はい、ありがとうございます。
本日はお集まりいただきましてありがとうございます。私、早稲田大学高等研究所に勤めております田中修と申します。どうぞよろしくお願いします。本日は先ほど株式会社リクルートコミュニケーションズの大石様からご紹介ありましたように、RCO スタディナイトの特別勉強会ということで D-Wave が切り開く量子コンピューターを活用する未来というタイトルの勉強会を行いたいと思います。で本イベントはですね、株式会社リクルートコミュニケーションズと D-Wave システムズ、そして早稲田大学高等研究所による共同開催という形で行わせていただいております。でまずはじめにですね、本日いらしていただきましたお三方にを紹介したいと思います。まず D-Wave システムズ USA プレジデントのロバート・ボー・ゴルチさんです。でもう一人が、D-Wave システムズ販売ディレクターのミスター・グレゴリー・ガブレニアさんです。で3人目がですね、D-Wave システムズのプロフェッショナルサービスディレクターのマーレイ・トムさんです。よろしくお願いします。でですね、まずはじめにですね、D-Wave の方々のお話をお聞きする前に簡単にですね、今回の趣旨についてお話をしたいと思います。でまずですね、前回今年の1月に開催した RCO スタディナイトで、これはリクルートコミュニケーションズにおける機械学習と次世代量子情報処理量子アニーリングというタイトルで1月に開催しました。150人を超す参加者の方々が集まりまして、それでスライドもですね公開してるんですけども、ものすごい閲覧数になっているという状況でございます。でこのようにですね、量子アニーリングというのは現在大変注目を集めている情報処理技術であります。そこでその量子アニーリングという技術の最も中心にいる方々、D-Wave の方々をお呼びして、本日はこういうセミナーを開催したということでございます。で D-Wave というのは皆さんご存知のように、世界初の商用量子アニーリングマシンを2011年5月に発表した会社です。 D-Wave という量子アニーリングマシンです。でこれがなぜ現在これほどまでに注目を集めているのかということなんですが、それはまさに現在ですね、ものすごく非常に多くの情報が、世界各地にありとあらゆるところにデータがあるわけです。でこれはいわゆる少し前の言葉で言えばビッグデータ社会、最近で流行りの言葉で言いますと IoT とかいろいろ な言葉が出てきているわけですが、いずれにしても大事なところは何かと言いますと、データがたくさんあったときにそれをどのように処理をしてどのように活用していくかということが重要なわけです。もちろん情報処理の中にはさまざまな課題、さまざまな問題があるわけですけれども、その中の一つとして今回量子アニーリングに取り上げる量子アニーリングが得意とする組み合わせ最適化問題というものがあります。組み合わせ最適化問題とは、膨大な選択肢があったときにどれが一番いい選択肢ですか。最も良い、最も効率の良い経路はどういう経路ですか。最も効率の良いシフト計画はどのようなものですか。最も効率の良い何々は、こういう最も効率の良いとか最も何々である、こういうものを探索するのが組み合わせ最適化問題なんです。このように非常に一般的な問題です。ですから非常に多くのアプリケーション応用があるわけです。まさにこれはたった一例でしかないですけれども、例えばシフト計画問題とか、他にもいろいろな応用例があるわけです。大事なことはいわゆる第一次産業、第二次産業、第三次産業といわゆる産業界、あらゆる産業界において組み合わせ最適化問題というものは内在する。産業でなくてもいいかもしれないです。つまりいろいろな人々の生活の中、暮らしの中にこういったその組み合わせ最適化問題というものは普遍的に内在するわけであります。でこの組み合わせ最適化問題を高速かつ高精度に解くことが期待されているのが量子アニーリングであるというわけでございます。量子アニーリングがまさにその物理学と情報科学が化学融合して出来上がったものだという見方ができると思います。もともとその物理学の言葉を使って情報処理を考えようという考え方、これはもう80年代から70年代からありました。すでにありました。もっと昔からありました。そういった中で生まれた一つの技術というのが量子アニーリングなわけです。1998年に日本の東工大の門脇さんと西森先生による理論的提案がなされました。それと同時にですね、この話とは全く独立しているところですが、いわゆる日本が少なからぬ貢献をしてきたそのいわゆる超電導エレクトロニクス、こういう技術の積み重ねがちょうどうまいことドッキングしてできた技術が量子アニーリングマシン D-Wave だったわけです。つまり2011年にですね、世界初の商用量子アニーリングマシン D-Wave が発表されたわけです。実際のところ2011年の5月発表された当時に比べて現在の注目度は飛躍的に上がっています。とするとこの2011年からその後に何があったのか、それを今日 D-Wave システムズの方々にお話を伺いたいというふうに考えていますし、また2011年よりも前にそういった量子アニーリングが注目される前触れがあったのではないか、こういうこともあるわけです。ですからD-Wave システムの方々にはいわゆるその歴史的なこともご紹介いただきますし、また現在その量子アニーリングというものがどのように注目されているのか、もしくはその将来展望はどのようなものなのかということをご紹介いただくということでございます。で本日の勉強会のタイトルにですねございますように、この活用するというところが私は極めて重要だというふうに考えています。まさにその D-Wave というマシン、量子アニーリングマシンが一応今あるわけです。あるわけですけども、これからどんどん進展していくというふうに D-Wave システム社の方は言っています。そしてそうなんですけれども、ただハードウェアがあるからいい、そういうわけにはいかないわけです。なぜならばこのハードウェアは何かに使えなければいけない、何かに使われるべきであるというわけです。そこで先ほど言いましたように、その組み合わせ最適化問題というものはですね、いろいろなその分野にですね広く活用されるわけなんですけれども、それぞれのその産業界、それぞれのお立場、それぞれの生き方、生活の中にそれぞれ組み合わせ最適化問題というものが内在しているわけです。もしくは今組み合わせ最適化問題と実際に起こっている問題が結びつかない問題も実はたくさんあります。そういった問題をそれぞれの方々が 量子アニーリングの話を今回 D-Wave の方々からお聞きして、それぞれが量子アニーリングをこういう問題に使ってみたらどうだろうか、もしくは組み合わせされているのはここにも組み合わせされているものがあるんじゃないかと、そういうようなことをいろいろ見つけていただければ我々主催者としては幸いに思います。以上で私からの初めに終わらせていただきます。ありがとうございます。続きましてD-Wave Systems USA 社長のロバート・ボー・イゴールズさんと、D-Wave Systems プロフェッショナルサービスディレクターのマーレイ・トムさんからのご講演があります。前半はUSA 社長のロバート・ボー・イゴールズさんで、後半はマーレイ・トムさんからのご講演というふうになっております。それではどうぞよろしくお願いします。
Can you hear me without the microphone, or should I use it? Probably.
Can't sound like without the microphone.
Okay, well, we'll see if this helps. So, how about that?
Yeah.
Okay. Well, thank you very much for hosting us tonight. We appreciate it. Looking forward to making many new friends. And I've seen some old friends tonight as we walked in from previous lives. I used to be the president of Cray Research, and our friends at Recruit had 2 of our computers many years ago, and we had many others in Japan. And then I was the CEO at Silicon Graphics, and so I've been to Japan many, many times, and it's very nice to be back this time helping D-Wave get started. So thank you for coming tonight. Thank you to our friends from Recruit for hosting us, and to our university friends for inviting us to come tonight. So we will talk a little bit about quantum computing, but I'm first going to back up and talk a little bit about how we got here, and then we'll specialize on D-Wave. So computing, in computing, there is a thing that we've been following for 50 years called Moore's Law. And this was the magazine in which it was originally published. Those of you who are younger, a magazine was printed on paper, and you would turn the pages, not electronic as it is now. And so 50 years ago, this article was published. And by Gordon Morse, basically saying that about every 2 years, every year, the number of transistors on a chip would be able to double. And so we've been riding that curve for many, many years, being able to make more powerful computers. But over that period of time, there also, it looks like now, Moore's Law may be coming toward an end of that doubling. And in fact, in the popular press, I think many of you know the European magazine, The Economist. The Economist every quarter puts out a technology review, and this was the latest technology review from The Economist, and it's talking about already after Moore's Law. So quantum computing is one of the things that will help us all after Moore's Law, we believe. Going the wrong way. So there have been many predictions, however, about the end of Moore's Law, and these are various times when people said Moore's Law would come to an end, including Moore himself, who said it would end in 2005, and then he later changed his ideas. But many, many people are now saying in the next 10 years or so, there will be a fundamental change in what we've been able to do. In fact, a person at Microsoft created a new law about the demise of Moore's Law. So this is Moore's Law's law, saying that the number of people predicting the death of Moore's Law is at least doubling every year, and I think it's doubling every week or every month, something like that. So, and jokes don't always translate very well, but this is intended to be a joke. So, And of all of the great companies that I have had the opportunity to work at, Cray Research, Silicon Graphics, and some other startup companies that we took public and did things with, this is the first of those companies that ever was on the cover of a popular public magazine or public press. This is Time magazine from the US. It's one of the weekly news magazines there. And about 2 years ago, they wrote a feature article about quantum computing, and they called our computer the Infinity Machine, and that was a picture of the chip that we were using at the time, and went to at great lengths to talk about quantum computing for the broad public, not just for technology people, but for the broad public. Background, quantum computing, the idea behind it really started with the famous physicist Richard Feynman. He postulated in about 1982 that using quantum mechanics, rather than fighting against quantum mechanics, that one may be able to build a computer. So the idea is 35 years old or so. And then the basic idea behind quantum mechanics, and Murray-san will jump down into the hardware and then show you how we program this machine. But the basic idea is that rather than fighting against quantum mechanics, as we have for the last 50 years in designing transistors and computers, we try to take advantage of quantum mechanics. And we'll show you how we do that. So in the traditional digital computer world that we're used to having bits, which are binary. They're a 0 or a 1. We're used to those bits being separable, and that each bit operates independently. And we're used to a world in which if we hit a barrier, whether it be on a transistor or if we're trying to do an optimization problem, we have to put more energy in to climb over the barrier to go down on the other side. And with the quantum computers, we're doing something different. And that is, first, instead of having binary bits that are a 0 or a 1, we use superposition, where our bits, we call them quantum bits or qubits, are a 0 or a 1 or both simultaneously. And with that, we can convey more information and search even larger spaces than we could normally. Secondly, we use the concept of entanglement. As we talked earlier, in traditional digital computers, the bits are all separable. And in our world, if we can get those bits to become entangled, I'll try to do this with the microphone. If we get these 10 bits to become entangled, then we no longer treat them as 10 unique bits, but rather they operate as a unit, and we need to think about them as a unit. And so they're able to do that. Oh, that won't be a very good picture. So we get them to operate as a unit rather than as independent bits. So that's entanglement. And then the one that's probably easiest to think about is quantum tunneling. In traditional computing, if we hit a barrier on, say, a transistor, we have to put more energy in to climb over that barrier. And in using quantum mechanics, we can actually tunnel through the barrier. And so we don't have to put more energy in. We actually take advantage of the laws of nature in which we're looking for the system wants to go to a lower energy state, and it does that by tunneling through barriers. So those are the three quantum mechanical effects that rather than fighting with, as you do in traditional computer design, we try to take advantage of. And we'll show you the results of that. So again, a little more background. The ideas behind quantum computing started with Richard Feynman. And then another man named David Deutsch said in about 1984, wrote a paper that in fact he created an idea about an architecture for a universal quantum computer. A theoretical architecture, but he laid out what that might look like. And from that idea, then people, including Deutsch, started writing some algorithms, theoretical algorithms, that would run on a theoretical, at the time, quantum computer. But some of those are algorithms that people have become well known. Probably the most well-known is Peter Shor's algorithm about quantum encryption, or decryption is what it really is, what the focus is on. And if one were able to run that algorithm, one theoretically would be able to decrypt most things that have ever been encrypted using RSA encryption as an example. To our knowledge, no one is able to do that. It's probably a long, long time before that happens, but that's the thing that people are both excited about or unhappy about as quantum computers come along. In research about quantum things, there is about $1.5 billion being spent every year on quantum research. And much of that, as many of you I'm sure know and are doing, much of that is on quantum communication, quantum keys, passing quantum keys, and a variety of device level things. And on the computing side, there are 2 or 3 different architectures that are being investigated. One of those goes back to the Deutsch's original paper about a gate model quantum computer, or a universal quantum computer. IBM just last week announced an experimental machine that they're making available on the web to selected people that has 5 qubits. And so it's a research machine, 5 qubits, but it is of this type of architecture. So, and IBM also estimates that it will probably be at least 10 more years before there would be a bigger working version of that available from them. Microsoft and others are investigating other architectures like topological and this one-way or cluster state. And D-Wave has focused on the adiabatic quantum computing. And that idea of being able to do an annealing type of computer actually goes back to a paper that was written in 1953 by Nick Metropolis and Edward Teller and the Rosenbluths at Los Alamos. And they had an idea that you could sort of by hardening and then relaxing conditions, and doing that over and over again, much like you would do annealing of steel if you were making a sword blade, heat it, beat it, cool it, heat it, beat it, cool it. The idea was maybe you could do that on a traditional computer, simulate annealing, and be able to get certain types of results better than you could in a normal type of calculation. So it's an old idea. And then that idea was updated in the late 1990s by our friends at Tokyo Institute of Technology, where we'll be tomorrow. So in 1998, Kawawaki-san and Nishimori-san wrote a paper, or released a paper, about being able to do quantum annealing, a theoretical paper, but it really formed the basis of what D-Wave then picked up and was able to build. And the next year, there were some people 2 years later, there were some people at mostly MIT who further refined that idea. And that was about when D-Wave was getting started 17 years ago. The company was started by 2 young PhD physics candidates at the University of British Columbia, and they had just taken a course on entrepreneurship. And they said, let's start a business. What do we know anything about? And they were physics students, and they said, we know some things about quantum. So let's start a business to do something in quantum. And they started collecting patents. This is true. They started collecting patents, and I think thought initially they could create a business by licensing patents. As many of us know from other companies and lives, that's a good idea. Sometimes it's harder to do than you think. But then they hit upon these ideas that maybe you could actually use quantum devices and build a computer. And so they started thinking about what would the architecture of that machine be, how might you program it, how would you represent, would it solve problems in the real world? And they came to the conclusion that yes, you could do that. And then they started hiring people they hired a mix of people who were physicists, but also started hiring some engineers. And Murray-san, who will talk next, is an engineering physicist, and he was one of the first people hired at the company. So he is our senior member, and even though he started working at the company when he was about 10 years old, as you'll see in a second. And I'm making a joke about how old I am compared to how young Murray-san is. Not a very good joke, but it's supposed to be a joke. So they started hiring people who were more engineers, and lo and behold, were able to create, about 5 years ago, the world's first quantum computer that was sold to Lockheed Martin, as we know. And basically, what they did was created a computer that is hugely different than anything we have ever known before. And a representation of the problem that that machine solves is this Hamiltonian. And we'll talk a little bit more, Murray-san will talk a little bit more about that. And that's basically what this machine is solving, the problem this machine is solving. It does it without adding any numbers, without subtracting any numbers. It solves something very close to that equation. And the way to think about this machine is that if you have a problem that you could map to, in this case, a three-dimensional landscape, mountains and valleys, it's really an n-dimensional energy landscape. But think of it as a three-dimensional landscape with mountains and valleys. What it does about 10,000 times a second is it finds the lowest valley or valleys in that energy landscape probably. It's a probabilistic machine. In the quantum world, things become probabilistic rather than deterministic. And so typically, instead of running a problem one time, you'll run it 100 times or 1,000 and get a distribution of answers back, at least with our type of machine. So a way to think about it simply is energy landscapes and finding the lowest valley or valleys in that energy landscape. This then is a start of what the machine looks like. We have 3 customers today. So Lockheed Martin was the first customer. 5 years ago, they bought the first D-Wave machine that had 128 qubits. Then about 2 or 3 years ago, they upgraded it to 500 qubits. And most recently, they've upgraded it to 1,000 qubits. Greg Son, who is with us, has been with the company about 5 years, and he looks after Lockheed Martin and Google and our customers on the west coast of North America. And then also we've asked him to help us as we start now working in Japan and lead our efforts here. Then secondly, Google became the second customer, and they bought their first machine almost 3 years ago now. It started at 500 qubits. It's been expanded to 1,000 now. And their machine is housed at NASA Ames in Silicon Valley, which is right next to the Googleplex, so they share the machine. And then Los Alamos National Lab became our third customer when they ordered a machine from us last fall. They've been running on it in our factory, and it's just being installed right now. It shipped this week, in fact, to Los Alamos. So 3 customers. Our customer base grew by 50% last year, from 2 customers to 3. And so it was an astounding growth rate, and we'll hope to continue that at some point. That was another joke, by the way. And so basically with what this machine, the problem this machine solves of mountains and valleys, finding the lowest valley, that sounds a lot like an optimization problem. And it's a particular type of a discrete combinatorial optimization problem that Murray-san will talk about. And then Google believed that you could also apply the machine to machine learning or some deep learning techniques. And we'll show you an example from that. They've had some success, and again, they've upgraded from 500 to 1,000 qubits. And then it also looks like it might be good at Monte Carlo or sampling sorts of applications. Of course, places like Los Alamos are the home of Monte Carlo. So we think there will be developments across all 3 of these areas. But it's very early in the development of these machines. So with this chart, I've tried to contrast what we do to the traditional world of computing that we're used to. In the world of the Intel 64-bit architectures, we're used to measuring performance in flops, floating point operations per second, billions of floating point operations per second. The D-Wave does 0 flops. It doesn't add or subtract. It does no floating point operations. Secondly, we're used to a world of 64-bit precision, 128-bit if we're using double precision. The D-Wave machine has about 5 bits of precision. So as you specify this energy landscape, so far at least, there's not a lot of dimensionality to it. It's relatively limited. And instead of doing billions and billions of instructions per second, our machine does about 10,000 instructions per second. But each of those instructions is solving this, looking at, with today's 1,000 qubit machine, is looking at 2 to the 1,000th potential solutions and evaluating all those and finding a low energy solution to the problem. So it's quite different. An Intel machine might have about 500 machine language and assembly language instructions. We have one instruction, but it's really a good instruction. And in that one instruction, you basically pack into that instruction the energy landscape that you want to solve. So for those who are computer science or computer engineering people, this is a really, really, really reduced instruction set computer with just one instruction. It operates at near absolute zero. Murray-san will show you that. In fact, it's probably the coldest place in the universe. The coldest place that astronomers have measured in the universe is about 1 Kelvin, a galaxy far, far away. And our machine runs at about 15 millikelvin. And it's superconducting. It uses virtually no power for the operation of the chip itself. However, we use about 25 kilowatts total for the operation of the refrigeration and the connection to the network and those sorts of things. So it probably uses less power than we were consuming in this room tonight. And we're up to 1,000 qubits. And this last line is intended to say it's really new days, new time here. This is what it must have been like in the 1950s at IBM or Fujitsu, where they were just switching to transistors. They were switching to core memories from storage tubes. Fortran hadn't been invented yet. There were no math libraries, no graphics libraries. If you wrote an application for one of their machines, it was probably the first time that had ever been done. That's where we are today. If you write an application for our computer today, it's probably the first time that application has ever been written or run on a quantum computer. So that's very exciting and fun for a lot of people. But if you're running, off-the-shelf third-party applications, that's not our world yet. Our world is more research and experimentation, and we need more smart people using our machine and creating software tools for it, so we'll be able to have more applications as we go forward. So this is what the machine looks like, and at this point I would turn it over to Murray to talk. And again, if you have questions, please feel free to ask as we go along. We'll also be here afterwards, and we'll try to answer any questions you have. So thank you very much. We appreciate being here.
こんばんは。ありがとうございます。Shimizu-san for hosting us here tonight, and Recruit, and thank you for taking the time to come and listen to our presentation. So in my portion of the talk, I'm going to talk about the hardware and show you what it looks like and the inside, and then we'll talk about what it would be like to program the quantum computer. How do we interact with it? Then we'll talk about two application examples, two small application examples, where we'll look at the steps that we can take to create an instruction for one of these quantum computing systems. And finally, I'll finish with about 4 slides to talk about performance tests for quantum annealers, testing against classical computers. This is a photo of our laboratory in Vancouver, and there are 3 quantum computing systems in this picture. Each of the rooms is about 3 meters across, 3 meters long, and about 3 meters tall. So they're quite big rooms. But inside each room, there's only one quantum computer chip about the size of our thumbnails. In front of the quantum computer system, there are 3 racks of equipment, and these are used to create the environment for the quantum processor. Two of the racks house pumps and compressors for the equipment inside, and the third rack has an application server here. And with an internet connection, we can actually send a problem from here, from a laptop, to the quantum computer. It can solve our problem and send the answers back. So when Boson was talking about the 25 kilowatts of power consumption for a D-Wave quantum computing system, it's the equipment in front of the system that's consuming almost all of that power. Now, if we walk up to the big room and open the door and look inside, then this is what we would see. A lot of shields and cans around the quantum processor. And this is because quantum mechanics is very delicate and easily disturbed. So even if a single photon hits a qubit, it can change its state. So there are 16 layers of shielding between the outside world and the quantum processor shown here. And the large room itself are 2 of those layers of shielding. Now, if we have an engineer here to remove the shielding in the cans and show the internals, then this is what we would see. It makes me think of a James Bond, Dr. No death ray apparatus. Vaguely menacing. There's a lot of science and technology that went into building this system to enable us to test the quantum processors inside them. And I'll just talk about 2 of those components. The first is reducing temperature. This is a photo of an ultra-low temperature refrigerator. If it were operating, we could touch this plate. It would be at room temperature. 2 plates down, this is at 4 Kelvin, the temperature of interstellar space. And another set of plates down here, we're at 0.015 degrees above absolute zero. More than 100 times colder than interstellar space. And all of this equipment and the quantum processor itself are at that temperature. The second component is that there are wires running down the refrigerator that carry the quantum machine instruction to the processor. And those wires are made out of metal that can superconduct at low temperatures, which means that it can carry a current without producing any resistance and no heat. At low temperatures, resistance will produce heat, and heat is noise for the quantum processor. And that's the reason why the quantum processor consumes virtually no power in the operation of the computer. Now, if we zoom in here at the bottom of the system and take off that cap, then we can see the quantum processor. And this is what it looks like. This is a photo of the D-Wave 2X 1000 qubit chip. This is beginning to look a lot more familiar for those of us who have taken apart our home computers and broken them, because this is what classical computer chips look like. And that's because we use very similar fabrication processes for making the quantum processors. So we have layers of metals and insulators to make the circuit. And the difference is that metals can superconduct at these low temperatures. Now you can see, because the projector is beautiful, that this has a square pattern in the active processor area right here. And if we were to zoom in on one of those small squares and enlarge it, then this is what we would see. So now we've taken a tour from the system at a large scale, and we've walked into the internals of the system. Here, we're down at 300 microns across in the circuitry. So in a classical computer, the fundamental building block is a transistor. Very much like a light switch. When it turns on, that's a 1 state, and when it turns off, that's a 0 state. Our quantum bits are made of loops of superconducting metal, and their 2 states are circulating current clockwise and circulating current counterclockwise. I'm just going to do something with my hands here. So if we take that loop and we draw it out like an elastic into a long, narrow loop, then that is shown in this picture right here. That's 1 qubit. And there are 2, 3, 4 qubits horizontally. And then vertically drawn out, there are 5, 6, 7, 8 qubits inside the unit cell. Now, a loop of metal with a circulating current has a magnetic field passing through the loop, up through the loop or down through the loop. So it's very natural to think about these fundamental building blocks like a bar magnet. North up is the 1 state and north down is the 0 state. And we all know from playing with bar magnets as kids that when we bring them close together, they have a very strong interaction. They want to oppositely align with one another. So where these 2 qubits cross over, there's a coupler between those 2. And you, as the programmer, set the coupling between those 2 qubits. Now, inside this unit cell, there are 1, 2, 3, 4. Hachi, Juni, Juhachi. Couplers, so 16 couplers total. And if we set all of those couplers so the qubits want to align with one another, then that's a very easy problem to solve. All the qubits should be up, or all the qubits should be down. But if we set some of the couplers so that the qubits want to anti-align, now there's frustration among the qubits. And that's what makes, frustration is what makes the high points in the landscape that you program. And where the couplings aren't frustrated, that are the low points in the landscape that the quantum processor is going to find for us. So even looking at the circuitry of the chip itself, we can see that this is very different from a classical computer. At this level, a classical computer is trying to add numbers together or multiply numbers together. And we can see that this processor is trying to optimize a network of interacting binary variables. And you'll see in all of the applications that feature is part of the application. That's where a quantum computer today is applicable. If there's no need to optimize a network of binary variables, then that may not be a good fit for a machine of this type. So now let's step out of the physical world and think about the programming world. There's 2 main things I want to say about the programming environment. The first is that all quantum computers will be accessed through a classical computer. So we'll be programming and doing analysis on a classical computing system in C or in Python, and then using that to communicate the instruction to the quantum processor. And once we've done that, that packages the quantum machine instruction, the QMI, and passes it to the quantum processor for us. So far, we've been talking about the processors, the quantum processors at the hardware level, and creating a quantum machine instruction directly onto them. And we have some application programming interfaces, APIs, in C, MATLAB, and Python that programmers can use to interact with the machine. But what we've been developing most rapidly now is a software development environment to enable programmers to be more productive at using these quantum computers. So specialized languages as translators to make it more compact programs, and then intermediate representations for the problems, and also some programs that can take problems that are too large for the chip and break them into pieces and solving the pieces one at a time on the quantum processor. Now this is the mathematical equation that Bo-san put up on the board. This is the problem that the D-Wave quantum processor solves. And it uses physics to solve this math equation. At this level, we don't need to worry about quantum mechanics. We can forget about Hamiltonians because we're programming classical problems that have classical solutions, and the quantum computer is using a quantum state to find those solutions for us. So here, to define some terms, the Q's are the qubits in the processor. And where there are two Q's, that's where there's an interaction between qubits through a coupler. You can set a weight for our qubit. If the weight is positive, that will push the qubit to want to be off, to be 0. And if the weight is negative, like a helium balloon, that will pull the qubit to the 1 value. So those are the programming biases that you can set. And the coupling strength determines if the qubits will be off or on together. So with a positive value here, the processor is trying to find the lowest section of the valley. That's the most negative number. So the way to lower a positive value is to make it 0. So one or the other or both qubits will take a 0 value. But with a negative strength, then the quantum processor wants to find both qubits to be on, so that that will contribute a negative number to this objective. So we can read this math equation in an application context. So imagine that we want to optimize a financial portfolio so that the best portfolio is at the bottom of the landscape. So we can use our classical computers, analyze investment data, and when we find the assets we want to choose that we think have the best value, we can make them low in the landscape so that those qubits will turn on and say, choose that asset. But if two assets in the portfolio respond to the market exactly the same way, so they rise and fall together, then they'll add risk to your portfolio. So in that case, you want to choose a coupling so that only one or the other qubit is on and chosen. So that is the objective, is to find the optimum portfolio given the weights and the strengths, and the quantum processor will find the portfolio, the zeros and ones, that finds the lowest point in this landscape. Once you've found those A's and B's, that is the quantum machine instruction. And for the D-Wave 2X, there are 4,512 of those parameters. So it's one instruction, but it has a lot of parameters. And you pass that to the quantum processor and tell it, I would like 10, 1,000, or 10,000 solutions. And the quantum processor can find each of those solutions and then return them to you. And as Bo-san was saying, though the problem is small, it's only 4,500 numbers, and the solutions are just 1,000 zeros and ones, also very small. The space of all possible solutions, 2 to the 1,000, is larger than the estimated number of particles in the universe. So it's a very complex problem. So now let's look at an example of an application that we could program on the quantum computer. And this example is to color the map of Canada so that each region chooses one of 4 colors, and it doesn't take the same color as any of its other neighbors. So there are 4 key steps to solving this problem, and the first step that we'll take is, actually before the first step, we'll observe that this has another big brother problem, which is coloring a graph represented here. So in this case, the one region, British Columbia, that's where I live. That's my home right there. And if it has a neighbor, an edge with Alberta, that means that they share a boundary. So now what we need to choose is an encoding between the colors and the qubits, the variables in our problem. So here, we'll choose one where each color gets a qubit. So a blue qubit, a green qubit, a red one, and a yellow qubit. And we're going to use those weights and these coupling strengths so that one and only one color is selected. And we're going to create this small objective by this equation here. And I'll skip a couple steps to show you that all of the weights are -1 and all of the coupling strengths are +2. And that's the way that we can set this relationship so that only one qubit will be selected. Now, this is possible to do by hand, but we also are creating software to allow programmers to automatically create these equations. So the second step is, now that we have our constraint, we have to put that into the processor. So before, I showed the qubits as long lines, and here, a qubit is a dot. And where 2 qubits have a coupling between them, that is shown by a line here. So the first thing you might notice is that if I put the blue qubit here and the green qubit here, there's no edge shared between those 2 physical qubits. So I'm going to choose an embedding where I take 2 physical qubits to represent one logical qubit here. So these 2 will be blue and these 2 will be green, and that will give me the coupling edges I need to embed this other graph. Once we have British Columbia, or any of the regions, into one unit cell, we can use the neighboring unit cells to the side, or above and below, to put the neighboring regions. So if we put a neighboring region, Alberta, to the right, we can use the couplings between those unit cells so that qubits will take opposing values. Also, if we have a region that is above British Columbia, but also needs to be above Alberta, we can actually copy these unit cells by using those couplings in the same way so that all of the yellow qubits will come on together by cloning them. So with those 4 steps, finding the encoding, the embedding, and then having interactions between regions and copying regions, those are all the steps we need to tell the quantum computer how to color a map. So I have a web browser that I've used to actually send an instruction to the quantum processor. And after the presentation, we can take a look at that and I can show you how the solutions have come back. But for now, what I'll go on to say is that when we need to work on problems that are larger than the chip, there are new programming techniques being developed. I would say new for quantum computing. We're adapting the techniques that are used in classical computing for solving these problems today, so that we can break large problems into chunks and solve each chunk on the quantum processor and then move to the next chunk. And using techniques like this, we've been able to move up to larger maps and larger ones still, coloring here all of the counties in the lower United States. As well as breaking large problems into pieces, we're also working on developing languages like constraint satisfaction languages so that we can make programming these problems more compact. And here we've managed to reduce a almost 600 line C code down to about 25 to 30 lines of code, where this language then takes the constraints. Alberta cannot be equal to British Columbia, and then it turns that down into the instruction that passes to the quantum processor. And it's the development of those tools that we've seen have made a big change in terms of the speed with which people can learn how to program these quantum processors. So now I'll talk about one other problem, just quickly, and three approaches that we've used for attacking this problem with a D-Wave quantum processor. The traveling salesman problem, one that we're very familiar with, is if you want to visit a large number of cities, how do you cycle through all the cities so that you have the lowest cost? And that low cost could be the time that it takes, or it could be the price of the tickets. So the first approach was to directly embed a small traveling salesman problem into the chip. And the way that this was done was that each qubit, instead of representing a city, it represents a move between cities. And that way, we create a constraint which is that only two of the edges leading to a city can be on, so that the edge that you walk into that city on and the edge that you take leaving the city. And that allowed us to fit a 4-city traveling salesman problem into the chip. Now our colleague Denny, who is probably the person who's tried the largest number of quantum algorithms in programming these systems, then looked at a technique that was borrowed from sorting networks. In a sorting network, you can take an ordering of numbers or cities on one side, and as they pass through the network, if a switch is turned on, it will exchange the order of the cities. And the network is designed so that any permutation of the cities can be made on the other side of the network. And that has allowed him to program a larger network of 16 cities using only 65 qubits. The next technique that he tried and developed was called parallel updates. And this allowed him to work with groups of 100 cities, where as he was optimizing the cycle, he would grab small groups of cities and place them into one small group on the quantum processor and do several of those in a single quantum machine instruction so that he could do a parallel update locally across the map. So through that development of techniques that Denny's been working on, we can see that the approach we use for taking applications and bringing them down into quantum machine instructions is changing and allowing us to work on larger, newer problems all the time. So with this, I'll finish with our final 4 slides. This was a performance test that Google asked us to do when they were considering purchasing our D-Wave 2 processor. And in this test, the size of the problem in the number of variables or qubits is along this axis, so from small to large. And the time it takes to solve the problems in the median case is listed on this axis here. This is 1 millisecond. That's 1 second. And this 1,000, that's 20 minutes per problem. So a very large Y scale on time. And what they found was that the D-Wave processor, shown here in red, compared to commercial software and publicly available software was 11,000 times faster at the largest size. And this was significant for two major reasons. The first was, this was the first time a quantum computer had ever beaten a classical computer at any test. Before this, people were factoring 15 into 3 and 5, and no one was timing those tests. The second point is that the D-Wave 1 system at this size was slower in this test. So in 2 years and one product generation, we went from slower than commercial software to 11,000 times faster than it. So this told Google, if that math equation is an important part of the optimization or machine learning problems we face as a business, then we have an opportunity to be solving them much more effectively with this technology. And we met with their director of vision search. He was working on a problem of taking images and identifying if there was a car in the image. And he was using the same mathematical equation to train computers to identify those cars. And we worked with his team for 6 months or so and adapted their techniques. And when we did, they found two important changes. The accuracy of those classifiers from their traditional methods went up from 84% to 94%. And the second was that the size of the classifier that runs on the classical computer reduced by a factor of 3, which means that it needs less CPU cycles to calculate if there's a car in the image or not. And that's really critical for Google because they're really working on developing smart pattern recognition software that can be loaded onto mobile devices. And so if they need fewer CPU cycles, they need less battery power, which means they're more effective in mobile applications. Just recently, in December, about 6 months ago, Google ran a new test, which was an attempt to show how can these quantum computers perform in the future. Right now they're working on problems of 1,000 variables, but what about when we get up to application scale problems? Well, they knew that in application scale problems, these landscapes would have barriers all over the place. So they synthetically created a small problem with lots of these barriers. And they ran it on the D-Wave quantum computer system, again, with problem sizes that are small going to large, and also on 2 classical algorithms, simulated annealing and quantum Monte Carlo, shown here. And what they found in December was that the time difference between the D-Wave system and these classical algorithms was 100 million times faster. That's probably the biggest difference we're ever going to see in a test, because it takes so much longer to run on classical resources, so many more classical resources to show 100 million times difference. But what we hope to see as the technology and the programming develops is that those problems will move from synthetic problems to more application-oriented problems as the technology gets larger, more mature, and the software and algorithms develop. My last slide, I'll just say I was asked about 2 or 3 years ago, what sets D-Wave apart from other companies and other universities who are trying to build quantum computing hardware? And there's a number of answers to that question, but probably the key one I would focus on is that we've been able to, over the last 10 years or so, double the size of our quantum processors consistently every 18 months or so. And that's very much like Moore's law for classical computing. It's a comment on our abilities to, as humans, not just the D-Wave, to put higher levels of integration into chips. And what's distinctive is that in other models of quantum computing, there may be larger ranges of problems that we can solve, and they may be able to test very interesting different areas of physics. But what we've seen from the development is that it's very challenging just to add 1 or 2 additional qubits to the processor rather than trying to consistently double them. And that's an important consideration for D-Wave because our focus is on solving commercial problems and helping our customers and partners to find value in these systems. Thank you very much for your time.
ありがとうございました。質問とかいろいろお聞きしたいことたくさん皆さんあると思うんですけど、たくさん時間ありますので、皆さんもしお聞きしたいことがありましたら挙手していただければと思います。大丈夫です。
マイクでお願いします。
わかりました。
貴重な話ありがとうございました。その D-Wave を使って量子コンピューティングをしたときに強みになるものっていうのが、紹介していただいた例ですと、例えば4色定理だとか、セールスマン問題だとかってことがあったと思うんですけれども、ついに認識としては、最適化問題に関する問題が、D-Wave では得意っていうふうに認識していていいんでしょうか。それとも要するにグラフ理論ですね。グラフ理論に関わるような何かそのテーマに一番フィットしているっていうふうに考えていいのか、それとも他にこういう強みもあるんだというようなストロングポイントがあればもしあれば教えていただきたいんです。
Thank you for your question. So yes, these 2 examples focused on optimization. And one point that both Thom made that I'll just reemphasize is that while we originally designed the system to optimize problems, to find the lowest points and valleys of the landscape, the machine naturally draws samples from that landscape. And that allows it to be used for other kinds of simulations if you want to simulate risk, like also in risk in financial securities or among communication networks where there might be failures in nodes in the network, and those failures are correlated with each other. And also for applications in machine learning and deep learning. And it's very natural to think about the quantum processors as a quantum mechanical neural net. And in a lot of machine learning applications, you need to be able to draw samples from these neural networks in order to be able to train the algorithm. So those are probably the 3 I would emphasize in terms of application.
なるほど、ありがとうございます。大丈夫ですか。たくさんの要素があった中でその関連付けっていうのを考えていくっていう点からすると、私今、生物系の仕事っていうのが多くなるんですけれども、その生物分野に何かチャレンジしていくっていうような取り組みっていうのはありますでしょうか。
Yes, absolutely. And in fact, those are some of the most exciting. Particularly when we think about machine learning, it's natural to think about applications for machine learning are where we're trying to use computers to help us with data analysis, predictive analysis tasks. And in biology, there's a lot of applications where we have a vast amount of information, genetic information or molecular information, that is difficult to find patterns in. So we actually have a project with a nonprofit organization at Stanford University who are looking at techniques for early cancer detection research and looking for approaches using the system for analyzing data to help with that effort.
ありがとうございました。Thank you very much.
他何かありますか。
商用といった面を強調されていましたが、いくらなんでしょう。
I should pull up the Time magazine slide because they actually set the price of the machine when the That's right. So the cost of the machines is the list price is about 15 million US dollars. But since Time magazine published this magazine, they set a street price for quantum computers at $10 million.
Ah, わかりました。ありがとうございます。
You can also lease them.
Okay. I should also mention that you can also lease the machines. So
You don't have $10 million.
$10 million. That's right.
すごい、面白いお話ありがとうございました。先ほどの4色の国旗の、国の塗り分けの問題で、例えば2色に塗り分けることはできないと思うんですけれども、量子的な量子コンピューターへの計算で失敗ってどういう状態なんでしょうか。
That's a great question. So in fact, the NP-hard version of the problem is that if you're given a graph, can you color it with only 4 colors or 5 colors? So it's been proven that a planar map can always be colored with 4 colors. And in fact, with the map of Canada, you can color it with 3 colors. But you can't color it with 2 because there are areas where you have 3 territories that border one another. So if you created that constraint that each region must pick 1 of 2 colors, and that neighbors can't pick the same color, and you call the quantum computer, each time 2 regions took the same color, it would see a penalty. And so it would try to minimize the number of penalties it saw over the whole map. And so while you would have borders with the same color, the goal would be for it to find the smallest number of edges with same colored regions.
ありがとうございます。
先ほど、手を挙げていた
ありがとうございました。金融機関が、こうした量子アニーリングのコンピューターに、興味を持っているという話はありますでしょうか。
So they are interested, as well as visiting Japan. I do actually spend a fair bit of time in New York. I was actually there twice in April. And also one of our investors in D-Wave is Goldman Sachs. And they are very interested in applications of this type, both optimizing strategies, but also estimating risk. And I would say we're both D-Wave and several individuals in finance are looking at ways of programming the system, given all of the expert knowledge in the field. In fact, we've just announced a new website called www.quantumforquants.org, which is actually intended to be a place for financial experts to pose problems and collaborate on finding programs for this machine in that space. Yeah, and this week there's a global derivatives conference in Budapest, Hungary, and another team of our colleagues are at that conference meeting with people right now.
Thank you very much for the great presentation. I am Tadashi Kadoaki, who wrote the first paper of quantum meeting with Professor Nishimori. So I'm very curious about the first, the physics did a great contribution to the quantum computer. In the future, the quantum computer, how you guys contribute to the basic science, for example, the measurement program or the basic quantum mechanics concept. How do you think about it?
Kadoaki-san, great to meet you. So I would say one way to look at the mission at D-Wave is to turn quantum mechanics into useful work. And when we did a scientific publication measuring entanglement in our processors, part of the reason that, a big part of the motivation for that test is that if you have a computer or a machine of any kind that can demonstrate entanglement and solve problems, then you can try to find a relationship between that phenomenon, the entanglement phenomenon, and solving problems well. So I think that there are a number of ways that we as a community are going to learn about physics through interacting with these man-made quantum mechanical processors. But a very important one for us is finding out how can we use them and harness them to solve information processing problems, both, I guess, in industry and in science. There are so many answers to your question. I'll talk to you brief, but the second one, I think, is that it's very difficult to theoretically show how these systems are going to behave as they scale, because they're not at zero temperature and they're in the presence of noise. So I think that as physicists who are studying spin glasses, they will actually get to see if they create barriers and frustration in these networks, how quantum mechanics responds to those. And I should pass it over to Thom as well.
Well, thank you for helping get us started. And, I would just add to that for a commercial company, D-Wave has published probably 120 peer-reviewed papers of one kind or another. So there's a long list of them on our website, and they've been published in Science and elsewhere, so there are many contributions, as you know. And then secondly, in the United States, in the IARPA agency, the Intelligence Advanced Research Projects Agency, they have just started a new project called Quantum Enhanced Optimization. And it's to work on the science underlying this type of computer. So hard to know who would win and who would participate in that, since it's a usual government call for proposals. But our expectation is that out of that program, whether it be D-Wave or perhaps some of our customers, that there will be more contributions to the fundamental science around what they're calling quantum enhanced optimization and what we call quantum.
貴重なお話ありがとうございました。量子コンピューターで今、例えば50年前はですね、今コンピューターが手元にあるということすら想像もできなかったんですけども、例えば今のスマートフォンみたいに量子コンピューターが我々の手に入ってですね、使われるようなシーンっていうのは果たして何年後とかどういった用途に使われるのか、ちょっとそういった柔らかい話をしていただきたいです。
That's a that's a great question. I think hopefully as many as possible of me has this to go.
Perhaps tomorrow or the next day. We would hope. That's a joke, by the way, unfortunately. The reality, of course, is that the way our machines are constructed, they operate at very near absolute zero. That's today something you probably cannot put in your pocket and carry around with you. So realistically, for machines like ours, it's probably a long time until until machines are in more customary environments rather than this enclosure. Having said that, the work on higher temperature superconducting devices continues apace, and at some point we or others may learn how to build qubits out of much higher temperature devices. The computer itself, as you know, it's no bigger than your thumbnail, so it easily could fit in a mobile device, but the environment that it has to fit in today is too harsh for us to carry around. So maybe next year, the year after, sometime soon we hope. But not joking anymore. The reality, I think, is as we work on the software tools and make them more robust, in fact, then there will be D-Wave machines on clouds, and so you'll be able to access them easily. The way that years ago our friends at Recruit made Craze available, I think at some point machines like ours should be available in the web like
that. Thank you for great presentation. Very interesting. Since I'm quite new to this research area, but let me try to ask two questions. Let me try my best to ask two questions. First one is, I would like to ask about the relationship between problem size and relaxation time. I assume usually there are two types of relaxation type as a physical implementation. And first one is could be energy relaxation, and second one is phase relaxation. And I have a feeling that phase relaxation time should be very faster than energy relaxation. And I'm afraid such fast phase relaxation breaks computation. So my question is there any typical problem size due to such related to such phase relaxation time, or is there any relationship between problem size and phase relaxation time? That's my first question. And the second one is, if that assumption is correct, I would like to know how do you control such fast relaxation?
Okay, great question. So let me just restate the question, which is that in quantum systems, if you open up a quantum state, it's not a 0-1 state anymore, it's more like a wave. And the phase tells you if you're on the leading edge of the wave or on the trailing edge. And that's a delicate quantum effect to keep for long periods of time. So when Peter Shor was writing his program for Shor's algorithm, he was using those complex numbers and storing information in the phase of the variable. And that allows him to put a lot of information into the qubits. But if the quantum state collapses, he loses that information. So he either has to correct that error or restart the algorithm. In our system, we're actually working in a space where the solutions are 0 and 1. And we're not putting information into the phase. So when we open up the quantum state, we're using the quantum state to change from the 0 to the 1. If the quantum state collapses, we don't lose information, but that channel closes. But with quantum annealing, if you hold it in the anneal, the quantum state will re-emerge and continue to change the state of the processor. So that's the reason why we have a 1,000-qubit processor that is solving problems with no quantum error correction. But even 5-qubit gate model quantum computers are needed to correct errors in their problem solving.
Thank you very much.
You're welcome.
Nick, thanks.
テクニカルな質問なんですけど、巡回セールスマン問題のウェイトのコントロールはどうやってるんですか？カップリングコンスタントのチューニングなのか、アルゴリズムで処理しているのか、どうなんですか？
So in the wait, so in the map coloring example, we had a constraint here amongst 4 qubits so that only 1 qubit would turn on. And the way we did that is we took the value of each of the 4 qubits and added them together. Qubit 1 plus qubit 2, red qubit plus yellow qubit. And then we subtracted 1. If only 1 qubit is on, then subtracting 1 should give you 0. And then by squaring that value, that makes 0 the lowest possible number that this objective can find. So I didn't show the constraint for the traveling salesman problem. But in the approach where we were doing the direct embedding, Albuquerque, the A city, has 3 qubits corresponding to a move from Albuquerque to either Boston, Charlotte, or Detroit. And so the way this was programmed is that a constraint was made between those qubits so that only 2 out of 3 could come on. And that requires that each time you move into a city, you can only move out through one other path. So that was how the constraints were made, but I didn't show you the A and B values for those constraints. But now we use software. If we want to choose 2 out of 3, we use a program to take that constraint and give us the weights and strengths. It won't work for the whole processor, but when we use small constraints over groups of qubits, it works quite well.
Oh, お話ありがとうございました。ちょっといろいろ聞きたいんですけども、2つほど聞きたくて、1つはちょっと素因数分解を最小値問題に置き換えた場合の注目度っていうのと、あとはもう1つは QMI にマッピングするときに論理的にプログラミング言語をハードウェアメーカーとして作るつもりがあるかどうかということなんですけど。
Okay, so great question. Because Shor's algorithm is probably the most famous algorithm in quantum computing, I do find that a lot of people are interested in how that might be approached. And while we can't run Shor's algorithm on our quantum computer, there is a way to factor numbers using this machine. And we factor numbers up to 32,000, which is by far the largest number that's ever been factored on a quantum computer. But for people in the career of factoring numbers, that's a very pea-sized number. As well, if we were to build a machine that its primary use was factoring, it has a very limited marketplace. The second question about developing a programming language. So the quantum processor is a little different from the way we think of classical computers. We don't actually have an operating system that goes on the chip. And so if we were going to be developing, we are actively developing languages here, techniques for solving problems that won't fit on the chip, or maybe can't even be written down, like simulations of vehicles, constraint satisfaction problems, or some examples in machine learning. We're actively trying to develop those. Our customers and partners are as well, and there are third-party software developers who are creating sort of software development kits to make it easier to program the machines. And kind of like the early development of classical computing languages, we're hoping to see techniques like compiling instructions for a quantum computer starting to emerge from that quantum computing industry developing those toolkits.
Very good. So this is very early. Those of you who are even older than I am would remember that IBM didn't develop the Fortran compiler until 1957, several years after they had computers available. And this is similar. So we have prototype software. We're not arrogant enough to call them compilers yet. We're calling them translators. And the idea is, thank you very much, our real translators, but we're calling these pieces of software translators to translate in a prototypical way from a subject matter expert language down into this machine language. And we're also building on things that we learned in high-performance computing over many years. In addition to the importance of compilers, we at some point figured out that we had problems that were larger than we could fit in the physical memory of a computer. So we created virtual memory, and that's what this virtual cubo is here. We also created meta representations of a program, and that's what the cubo actually is here, is not the actual machine instruction, but is a meta representation of it. So many of the things that we learned before about creating languages, subdividing partitioning problems, creating virtual representations of problems, meta representations of problems, we're doing that again, and it will go more rapidly here, we believe. So but at the core, we need more smart people thinking about this machine for both applications as well as what the software tools might look like.
そうですね。あと数分なので、あと2、3個ぐらい質問いただきたいんですけど、はい。ちょっと結構ありますね。はい。じゃあそれぞれ短めの質問でお願いいたします。はい。
お話ありがとうございました。ちょっとアカデミックな話じゃなくてビジネスシーンの話を、させていただきたいと思います。ちょっと前までビッグデータ、今でいう IoT みたいな話の中で、今後そのデータ分析をしていく中で重要なのって、理算的なモデルを今時点で解析することに加えて、将来を推計していくことがあると思うんですけども、さっきのリスク分散のところ、リスク評価ですね、金融工学の話でいうアクチュアリアルな世界でいうと、分析って結局将来を推計することが最も重要なのかなというふうに考えていて、リスク要素をシミュレーションして将来のことを予測するというものは 今回お話を伺った中では比較的得意な分野ではないのかなというふうに認識したんですが、その認識がまず合っているかどうか教えてください。
Yeah, I think that is the correct understanding. That looking at predictive analytics, analyzing data to anticipate what might come out, and also risk calculations. Those are, I think, very good applications for these quantum computers.
他
Thank you for your interesting presentation. And my question is it possible to encode arbitrary Boolean satisfiability problem into QBO? We can use the D-Wave machine as a replacement of the solver. We can use very conveniently without knowing the detail about quantum mechanics.
Yeah, that is feasible for satisfiability problems that are small and complex at small sizes. We have actually done a study on a small variety of SAT variants. So they're called like exotic SAT problems.
Exotic SAT?
Exotic SAT variants. So rather than 3 SAT, not all equal 3 SAT, or 2 and 4 SAT. We've actually been testing them against SAT solvers like WalkSat and Prometheus. It's still early days, but the hardware seems to have a strong capability for finding diverse, satisfying solutions that might be challenging for a classical solver. So we'll see as that opens up.
Thank you.
Murray, you might point to the two examples just as a rough idea.
Oh yeah, and one of our approaches here is for people who are working in satisfiability spaces or constraint satisfaction spaces, is that we can probably express them more compactly with codes like 2Q to make it a little bit less of a process to write those satisfiability problems into quantum machine instructions.
Thank you for your impressive presentation. And every time when you solve optimization problem, the problem is, I think, the solution is a global solution or a local solution, and the machine can find the global solution every time, or you need to calculate some to find it.
So that's a great question. So in the map coloring example that I used, particularly with coloring the map of Canada, the quantum processor can find a global optimum solution multiple times. In fact, in the test we ran a couple of days ago, it found 73 different colorings for the map of Canada. But it's not guaranteed to find a globally optimum solution. So in fact, there are quite a few cases where we will actually get answers back from the quantum hardware, where it will very quickly find high-quality solutions, and then we'll pass them to a classical computer and have it do a local search around that. Because you can't take a solution from the quantum computer and give it back and say, you stopped here last time, begin again from this point. The quantum computer immediately erases its state and searches the whole landscape. But classical computers do that very well. And so there's actually a very good complementary capability to hybridize classical and quantum computers that way.
Okay, thank you.
どうも
巡回セールスマン問題を解いていたと思うんですけれども、パラレル、並列な処理をする際に解ける都市の数が上がっていたと思うんですけれども、それは分割した数だけ解ける都市の最大数が増えるのかということと、もう一つ、答えの精度が分割によってどのように上下するのかということを教えていただきたいです。
That's a terrific question. And that's absolutely a challenge. So in that technique, which was to grab like chunks of 8 qubits at a time, that allowed our colleague Denny to break the problem up into smaller chunks. But if the chunks get too small, they become trivial, and they're not contributing strongly to the overall solution. But that is absolutely a challenge with facing problems like these today with classical computers, which is if you had a 10,000 variable problem and you broke it up into 1,000 variable chunks to solve, how much better would it get if you could break it into 2,000 variable chunks? And it's been very hard to answer that question because even the 1,000 variable chunks are so hard to solve in classical computers. It won't be as efficient as having an enormous quantum computer which fits the whole problem in one shot. But that is, I'd say, in the process of finding the best solutions we can find with limited time, that is exactly how we're facing the problems now.
Thank you very much.
はい、じゃあ、すいません、もう結構時間もしてますので、まだまだ質問されたい方もいらっしゃるかと思うんですが、ここで一旦終わりたいと思います。最後に1点お聞きしたいんですが、結構皆さんいろいろお聞きしたいことまだまだたくさんあると思うんですけど、そういう場合ってコンタクトとかっていうのは気楽に取ることがOK なんですか。そこら辺をちょっとはい、大丈夫なんです。そのウェブサイトのそのコンタクトのところをあなたがあるんですか。多分結構まだ聞きたいことがたくさんいらっしゃるから、そこら辺の情報とかはアナウンス。
So a very good question. There are multiple ways to do that. One of those is sales at D-Wavesys.com. Another is murray.tom at D-Wavesys.com. And another is bo at D-Wavesys.com. So we're open. We may not be quite as fast because there are more of you, but yeah, we're very interested in communication and getting ideas on how to use our systems. And perhaps just one other point to the last question, and I don't think we brought this out very clearly. This type of computer, we do not envision replacing existing computers. It will be used side by side with existing computers. So if you're doing a complicated search, we may get you in the lowest valley, but we're not the best computer to find the lowest point in the lowest valley. So we would expect to use our machine, for example, to help find a good valley to search in, and then a traditional computer to do a more detailed search in that valley. And probably the same thing on machine learning. We'll get a good starting point for some things, and then perhaps a host data analytics computer with a lot of NVIDIA chips in it will be able to get to the more a final answer, perhaps. So thank you very much. We appreciate your time and your attention. And we'll look forward to making new friends, and it is so good to see some of our old friends in the audience again. So thank you very much.
続きまして株式会社リクルートコミュニケーションズの棚橋幸太郎さんからの話があります。
それでは、コンタマネーリング for Future Selection というタイトルで、リクルートコミュニケーションズの棚橋が、発表させていただきます。まず、なんでリクルートという、全くその、技術と関係なさそうな、しかも、D-Wave やその量子アニーリングと全く関係なさそうな会社が、こういったイベントを開いて、でまた量子アニーリングの研究をしているかということについても、お話ししたいと思います。で我々は、量子アニーリングを使った、機械学習のアルゴリズムを、開発したという話になります。でこの研究は、私の同僚の、高柳と、また、早稲田大学高等研究所の、田中修先生と一緒に行った研究です。でまず最初に少し、私たちの、会社について、簡単にご紹介させていただきます。リクルートコミュニケーションズは、リクルートグループの、一つの、機能会社でして、リクルートすべてのサービスを、デジタルマーケティングを通して、世界のユーザーに、届ける役割を、担っています。リクルートグループには、数百を超えるウェブサイトを、持っておりまして、これらを、最適なユーザーに、届けるといった、いわば一種の最適化問題を解いているような会社になっています。で、特に私が属している部署というのは、アドテクノロジーに関する、部署でして、オンライン広告の商品を扱っています。で、扱っているユーザーの規模としては、ユーザー数が13億で、広告のキャンペーンは2万3000を超えています。でこのような大きな広告のシステムを高い技術が支えています。で例えばハイスループットローレイテンシーなシステム、これは例えば秒間5万件以上のリクエストをさばいたり、50ミリ秒以内にレスポンスを返すといった処理が必要になったりします。またテラバイトやペタバイトスケールの非常に大きなデータを数時間で処理するようなシステムや、非常に高精度にユーザーをターゲティングするようなシステムが必要になります。で特に今日、お話しする内容というのはこの、オプティマイゼーションマシンラーニングについての話になります。特徴量選択という問題は、ご存知でしょうか。こちらの図がデータを表しています。データの行列を表しています。縦方向がデータ点、横方向がデータの次元と考えてください。例えばこのデータを使ってデータが例えばユーザーのデータだったとします。でこのデータ一つ一つの特徴というのはそのユーザーの特徴、例えば都道府県だったり、今までどういうサービスを使ってきたかといった特徴になります。でこれを使ってそのユーザーが例えばある商品を買うかどうかを予測したりするという問題が、あります。でこの時全ての特徴が重要になるわけではありません。ある特定の特徴だけが非常に重要に効いてくることがあります。でこの重要な特徴を抽出する問題というのがフィーチャーセレクションになります。でこれができるとどう嬉しいのかといいますと、例えば最もビジネス的に重要なファクターを求めることができたり、もしくは全てのデータを使う必要がなくなりますので、コンピューターのリソースを節約することができます。しかしフィーチャーセレクションというのは非常に難しい問題でして、なぜかというとこの特徴の中からどの特徴を何個選べばいいのかというのは非常に大きな数になってしまいます。でこういう問題を組み合わせ爆発と言います。すべての組み合わせを考えていると、普通の、コンピューターでは数えきれないほどの数になってしまう。例えば特徴数が、次元が20の場合だとこのパターンというのは100万を超えてしまいます。もっと大きな問題というのは普通にビジネスの現場に存在します。でこういった特徴選択の問題に対してもちろん、既存の、ソリューションというのがあります。で代表的なものとして L1 Regularized Logistic Regression というのがあります。 これは L1 ノルムというパラメータをできるだけ素行列にするようなペナルティ項を入れることによって、使わない特徴というのを削ぎ落とすようなアルゴリズム。しかしこの、アルゴリズムの、欠点として、線形のデータしか使えないという問題で、今回我々が考えたのは L0 ノルムを使った特徴量選択の問題になります。先ほど、説明しましたように、L1 ノルムと L0 ノルムというのがあるんですけど、この L1 ノルムと L0 ノルムって結局何なのかというのを簡単にご説明します。例えばここにベータというベクトルがあります。でベータというベクトルの要素は例えば 2.1 とか0とか 4.5 で構成されます。L1 ノルムというのはそれぞれのベクトルの要素の絶対値の和になります。その場合だと 7.6 になります。L0 ノルムというのはこのベクトルの0じゃない要素の数、つまりこの場合だと3になります。で既存のアルゴリズムというのはこの各要素の絶対値の和を最小化するような手法をとっています。でこれを行うことで、間接的に、0でない要素の数を減らすことはできるんですけど、純粋に減らすことはできません。一方 L0 ノルムというのは純粋にこの0じゃないベクトルの要素というのを表現しますので、特徴量を使う特徴の数というのは純粋に減らすことができます。しかし L0 ノルムを最小化するような問題というのは、コンビネーション、組み合わせ最適化問題になってしまいますので、普通の方法では解くのは非常に難しいでそこで、先ほどD-Wave の方が紹介してくださった Q ブーストという手法があるんですけど、これを元に我々は QAFS クォンタムアニーリングフォーフィーチャーセレクションというアルゴリズムを開発しました。でこの QAFS はいくつかの弱学習器から成り立っています。この弱学習器っていうのはある問題を予測、日分類だったら0か1、つまりあるユーザーが商品を買うか買わないかというのをランダムよりかはいい精度で当てるような学習器になっています。でこれを、組み合わせることを考えます。でこれを組み合わせて全ての、弱学習器が出した答えの平均を取ると非常に良い結果が出るという、こういう手法をアンサンブルメソッドというんですけど、こういった考えに基づいて QAFS ができています。でこの弱学習器一つ一つというのは一つ一つが、データの特徴と結びついています。例えば最初の弱学習器だったら、1と3という番号の特徴と結びついています。ですのでどの弱学習器を使うかっていうものを選ぶことによってどの特徴を使うのかという問題を間接的に解くことができます。でさらに弱学習器というのは非線形のデータに対しても良い、予測をすることができるものですので、非線形のデータに対しても、このアルゴリズムは用いることができます。そしてどの弱学習器を使うか使わないかというのは先ほど D-Wave の説明でもありましたように、スピンが下を向いているものに対応する弱学習器は使わない、スピンが上を向いているものに対応する弱学習器は使うといったように選択していけば、このスピンの上と下というものを選択することによって、最適なこの弱学習器っていうのを選択するような問題に落とし込んでいます。で何を最小化するかといいますと、まず全体の弱学習器で使う特徴の数、そして、この選んだ弱学習器が出した、学習誤差ですね、学習データに対する誤差を最小化します。この2つを最小化することで最も少ない特徴量で、良い結果を出すようなアルゴリズムを作りました。で我々はここの、スピンの最適化の部分をクォンタムモンテカルロ法によって、解きました。これは、古典的なコンピューターによって、量子現象をシミュレーションします。これは、古典的な手法ではあるんですけど、シミュレーティッドアニーリングよりも良い結果が出るということが分かっています。 そして私たちは D-Wave を持っていないのでこの MacBook で計算するためにはこれを使うことが、今のところ最良の、解決法だと考えました。例えばこんな問題を、考えてみます。ある、広告の商品、家とか車とかがあったとしますと、この車とか家というものには、ある特徴があります。車だったら車種だったり年数だったり排気量だったり特徴があります。でこの特徴からその商品がどのぐらい、購入されるか、購入率のことを CVR と専門用語で言うんですけど、この購入率 CVR っていうものをあるアイテムの特徴を使って予測したい。でさらにどんな特徴が高い CVR に貢献するのかっていうのも一緒に知りたい。そういう時に QAFS っていうのは限られた数の特徴を使って、CVR を予測するような、問題を解くことができるので、こういった問題を、解決することができます。実際に、リクルートの、ビジネスの現場で、から得られたデータに対して QAFS を適用した結果はこちらになります。横軸というのが選択された特徴量の数、縦軸というのが予測精度、AUC という指標になるんですけど、高ければ高いほどいいというふうに考えてください。そしてこの青い点というのが QAFS の結果になります。でこの緑の点というのは既存のランダムフォレストというものを使って特徴量を抽出するような手法になります。でこの丸い点は先ほど紹介した L1 ロジスティックリグレッションというものになります。ここで、まず最初注目してほしい点は、青い点というのは非常に限られた特徴の、使う特徴に対して、良い精度を出しているという点がまず一つ重要な点です。でもう一つは、青い点というのは、限られた範囲の特徴量の数の領域に絞られています。つまり緑の点、赤い点は非常に広い、特徴量の数の領域に属していますが、この例えば緑の点、赤い点というのは自分で使う特徴量の数を決める必要があります。これはハイパーパラメータと言われる、パラメータによってチューニングするんですけど、使う特徴量の数は結局自分で決めないといけない。ただし、この QAFS というのは使う特徴量の数まで、決めることができます。実際に、使う特徴量の数、今回15っていうふうにQAFS は示したんですけど、15よりも低い特徴量の数を使うと緑の点もこの赤い点も精度が落ちてしまう。でこれは使う特徴の数を減らすと十分な情報がないので精度が下がってしまう。で一方、特徴を使いすぎても乱雑な情報が入ってくるだけなので精度は落ちてしまう。でちょうどいいこの特徴の数というのを QAFS は探し出しています。でまた、シミュレーチッドアニーリングと、クォンタムアニーリング、量子モンテカルロによるクォンタムアニーリングの、損失関数の、グラフになるんですけど、横軸がこの量子揺らぎを制御するチューニングパラメータになりまして、このガンマ0を制御することによってシミュレーチッドアニーリングよりも非常に低い、損失関数を実現することができる。つまり損失関数というのは最適化するエネルギーですので、非常に低いエネルギーの状態に到達する、限られた時間で到達することができるということは示されています。以上、まとめますと、我々は、オンライン広告の商品を扱っています。でそこでは非常に最適化問題というのが重要になります。そして今、D-Wave が、話されたように、組み合わせ最適化問題というのが非常にエレガントな方法で、解けるような時代になってきていると。そこでどうにかこういった、組み合わせ最適化問題を使ってビジネスの場で非常に有効なアルゴリズムを作りたいというモチベーションから、 特徴量を選択するようなアルゴリズムっていうのを今回開発しました。でまたこの QFS は既存の、非常に良いと言われているランダムフォレストを使った手法や、L1 ロジスティック回帰よりも良い性能を出すことができます。以上になります。ありがとうございました。
ありがとうございました。花橋さんのご講演に関しましては後でですね懇親会もありますので、その時にいろいろご質問がある方はしていただければと思います。で発表は株式会社リクルートコミュニケーションズと早稲田大学高等研究所の共同研究によって行われて、AQC でも発表しますし、その他にも何らかの形で公開できればなというふうに考えております。では本日ですねD-Wave システムズの方々に大変素晴らしいご講演をいただきましたこと大変感謝いたします。もう一度拍手でよろしくお願いします。はい、それではお開きになります。ありがとうございました。
皆さん、最後、業務連絡だけ少しお理解いただければと思います。2点だけですね。